Good day. My name is Jay Wallstrom, a system architect for Micron and your host. I'd like to welcome everyone to the webinar hosted by Micron, where AI matters, getting to the heart of data intelligence with memory and storage. As we all know, AI, machine learning, deep learning continue to make headlines in the tech world. The truth is, we are still in the infancy of this revolution. Today, Forrester Consulting has concluded an extensive research project interviewing architects, IT, data scientists to understand their perceptions and challenges of AI architectures. Chris Gardner, senior analyst serving infrastructure and operational professionals, will provide insight on these findings. And as Micron works closely with customers and partners, you will also hear from memory and storage experts. Eric Booth, senior manager of data center solutions on memory, and Wes Baskey, principal storage solutions engineer on storage. We encourage you to IM your questions in the chat windows. We'll do our best to cover as many as we can for the time that we have at the end of the presentation. This is being recorded and will be available later on this afternoon. Thank you for spending your time with us. So now, let's get started. I'm going to turn it over to Chris Gardner, the senior analyst, to give us his feedback on the study that they have conducted. Chris?
Perfect. Thank you. Thank you for inviting me out here. So we're going to go a little bit deeper into, again, this custom study that we did. And I think what was really interesting about this is that there hasn't been a lot of studies yet around the memory and storage limitations that are in place and the kind of the impact that it has on infrastructure and operations professionals as they head down this road. We're going to primarily, first off, I'm going to give a quick introduction who I am and why you should be listening to me, but also a little bit of background on what we're studying here. Then the findings, which I think are really interesting and should hopefully prompt some really interesting conversation and discussions. And then finally some recommendations based off of what we discovered. So as an introduction, as it was mentioned, I serve infrastructure and operations professionals. I'm not going to read this. It's a bit of an eye chart, but what you need to know is that I used to do this for a living. I've been an analyst for a number of years, but before this, I was doing infrastructure and operations in large organizations. I was making many architectural decisions around storage and memory in particular. I was eventually moved over into the strategy portion to do some architecture work for the entire enterprise, and then finally doing some strategy in general. And what I've noticed is that there is definitely a trend and evolution that's occurring that folks need to understand in order to best architect for these new workloads, these AI and machine learning workloads. Now, just so we're on the same page, people tend to conflate these terms, and I wanted to make sure that definition-wise we were all in sync, right? So automation, just really quick, is essentially dumb machinery. In essence, it's commodity tasks that are repetitive in nature that some kind of an algorithm kicks off and runs. This is not a new emerging workload. Automation's been around for some time. It's, at this point, just about everywhere, and whether you see it in in a supermarket when you're checking out, or you see a driverless car drive by, which I just saw, very recently, it's here. Now, an emerging workload-wise, there's two different kind of realms around machine learning and artificial intelligence. Both kind of try to attack the same problem in slightly different ways. So machine learning is mathematical models, and these have been around for some time. It's basically a gigantic math equation that tries to predict the future. And it's well established in certain verticals, in particular finance. When you look at insurance companies, for example, they've been using machine learning models for some time to determine longevity of their clients and how they should price things and that sort of stuff. Artificial intelligence is a little more tricky. It's basically replicating what a human is doing in their brain. And it's deep learning. It's essentially trying to recreate and teach a program to act a little more like a human. There's new use cases every day. You've heard, obviously, of the ones like Watson and things like that for oncology as the greatest potential human impact. But right now, it's just at the beginning stages. Forrester has a list of emerging technologies that we study. This list obviously changes over time. But what you'll notice here is that everything that is in blue is essentially a AI or ML construct, whether it's deep learning, natural language generation, computer vision, et cetera. And what you'll notice is that some of these things aren't exactly new. We've been studying them for decades, but being able to actually get business value out of these things is a relatively recent phenomenon. And in order to squeeze more out of it, we had to ask questions specifically around how you're architecting to meet those needs. I want to also mention really briefly that if you're not familiar with it, there is a term or set of terms in AI and machine learning called training and inference. Training is actually teaching the thing. It's building out the models, studying a large data sets. It requires significant horsepower, and it requires fairly good latency on storage, fairly good connectivity and latency on broadband. When you talk about inference, though, that's using the models. That's actually saying, okay, if I have a security camera pointed at somebody, I can look at it briefly and determine, based off of the model that's already been created, who that person is. And you need significantly less power to pull that off. So hardware needs differ. If you're going to have a device at the edge, it's more likely to do inference. If you're going to have a model that needs to run, it's most likely going to run in a data center or in the public cloud. So let's dig a little deeper into what we were discovering here. And again, we talked to 200 folks that were basically responsible for architectures of very large mixed data sets. They were heavily involved in AI and machine learning, but they also had a lot of expertise about the hardware requirements and the concerns they had about that. How is AI and ML done today? 70% of the folks are using AI and ML to do complex data workloads, which is essentially things like data lakes, but also things like image recognition. The vast majority, if you ask them, are doing it in two major places. They're doing it on premises in local data centers. They're also doing it in a private cloud, again, typically on premises, but sometimes mixed with colos. Some of them are doing it, if you look towards the bottom, in the public cloud and the edge. And one of the findings that you're going to see in a second is how the placement is going to change over time and what the expectation is for that. If we ask people what kind of hardware they're using and where, 42% say they're using hardware specifically for training AI and ML models using only third-party cloud providers. So if a mega cloud provides a service to use like TPUs or GPUs, they're using that as the primary means for training today. If you look down this list, they're also doing, in a relatively small scale, the same type of engineering and work on premises, as well as even in some cases not even using specific hardware for this. So at this point, for a large number of folks, if they're going to be doing any experimentation at all in AI and in machine learning, they're going to be doing it with perhaps hardware that's not necessarily attuned for it, and if it is, it may be in different locations than what they're used to. What are they looking for? What's important in terms of hardware? 90%, or approximately 90%, say that it's critical or important for compute and memory to be close together. Now, what am I saying here? It's not just, when I say memory, I'm not just talking about the actual in-memory, like DRAM and things like that. I'm also talking about storage as well. What they're saying here is that they can't have compute be a distance away. They can't have compute being and running in a different data center. They can't have, in terms of data gravity needs, they can't have the data living in a different location like the cloud. It's hyper important that they stick the hardware for compute and storage and memory close to one another. And incredibly, or perhaps not, if you've been studying this as much as I have, most of them believe they need to re-architect. More than 90% say they need to re-architect memory and storage to meet their goals for training in the future. It varies a little bit in the sense that they believe that memory is, at the critical state, memory is a little bit more important than storage is, while in the important state, storage is a little more important than memory. What we tend to find is that most folks we talk to want to stay in memory for as long as possible, so this makes sense. But where the rubber meets the road in terms of actual business results, they're just not getting them today with their current architecture. And this was pretty interesting. We asked, in terms of challenges, hardware-related challenges, what are you seeing as problems right now? And I kind of expected, to be frank, that some of these on the bottom would kind of shoot to the top, but overwhelmingly, the top two things that they're concerned about is storage performance and available memory. They're worried about throughput, essentially, from these things. Close behind, tied for second, is the ability to actually leverage software to attack the hardware programmatically. But I think it's pretty interesting to see that it's not things like compute. That's up there, but it's not the number one issue. It's not things like thermal management. It's literally available storage performance and available memory are the top two concerns that people focus on. So what are they doing? What are they changing to address this? Well, not only are they concerned about it, they're making changes to move compute and memory closer to one another. So 90% of the folks that we asked are in the process of moving these things together to improve workloads. Only 8% are not, and 2% either don't know or did not answer. That's tremendous, and it basically says that the results are clear in terms of what architecture needs to be changed to in order to deliver the results they want to see, which, quite frankly, means moving things around. If we look at where they're accessing, or where they're analyzing, I should say, data sets today versus 3 years from now, it's pretty dramatic changes. Earlier I was mentioning that 72% are doing it in an on-premise data center and or in a private cloud, and that's going to shrink to as much as 44%, 40%. If you look on the opposite end of the scale, public cloud usage is going to increase about 10%, and at the edge is also going to increase about 10%. And if you recall what I was saying earlier about training versus inference, a lot of that edge work is going to be inference. Perhaps a bit of maybe not anomaly, but just an interesting side note is the relative shrink of doing it on IoT devices and on mobile devices. And I want to be clear that edge kind of encompasses these things, so it could be that folks are realizing that they can't quite get the performance they need out of IoT devices and mobile devices to do some of the work. That's why it's going to the edge, but I expect to see it balance out. The number one thing you need to know here is that it's a hybrid workload. It's essentially going to live in multiple locations at one time, and you're going to want to move these things around. And that comes out in the final results about where they're going to be doing these things. If you look at using hardware built for AI and machine learning, using only third-party cloud providers, this was pretty succinct in the sense that it was 42%, but they're only going to be doing 12% in the future. Where it's going, they're going to be using a combination of on-premises and third-party cloud providers. They're going to want to be able to move these workloads around, and that's where the programmability of the hardware comes into play, and also the ability to kind of transcend the data gravity and move it to locations that make the most sense. When we ask people, what kind of benefits do you expect to see if you do all these things that you're suggesting you're going to do? There's technical benefits and business benefits. Technical benefits are some things that you probably would, expect, right? They expect more flexibility by re-architecting memory and storage. They expect to see higher accuracy of results, bigger data sets, or models should complete faster. I want to be clear that we were very specific with this question. We did not say, if you increase these things, if you increase the amount of memory you have and storage you have, do you expect these benefits? We said, if you re-architect your approach here, if you move the actual hardware around and build around that, do you see results? And the answer is they expect to see is yes. But what's perhaps more interesting, at least to me, is the business benefits, right? So it's pretty easy to say, if I change my hardware, I should get technical benefits, or if I change my architecture or my hardware. But overwhelmingly, people also brought up additional benefits that are actually business-driven. They expect to see faster product innovation, time to market. They expect to have a better customer experience. And it's pretty universal for a lot of these. It's very close between inference and training, which means that they're sticking at both sides of the equation. in addition to things like fewer errors discovered by the customer, decreased costs, which are just basic concepts that a lot of us in the continuous delivery world are quite familiar with, trying to improve iteratively and rapidly for business results. And, we also did a number of interviews with some really high-end experts in this area, and they said this is what it's all about. It's great that we're going to get better technical performance out of this, but what I really want to see is better business results. So I want to be able to go back to the business and say, look how more accurate my analysis is and my predictions are. We can make more educated decisions about how we're going to change the product lineup, and it should impact and improve revenue. So lastly, I want to talk about some recommendations, and this came out through the data as well as some analysis that we've done around AI and machine learning hardware workloads in the past 6 months or so. First off, I think it's blatantly obvious, if it's not already, you need to put the workloads where they belong. And that means that if you happen to have things that are in the cloud or at the edge, you need to really consider if they should belong there. I'm not suggesting that we need to have a max exodus from one type of location for these workloads to another. I'm simply saying there needs to be a balance that needs to be struck. It needs to be a hybrid approach to where you're going to store these various pieces. Again, another thing that came out very clearly in the data, you need to re-architect memory and storage around throughput and performance. This also came out in the interviews. It was very, very clear that while they were fairly happy, most of the folks we talked to, with the compute performance, what they had at the time, they were not happy with memory and storage performance and how it was architected. It's a little difficult to buy off the shelf, and I want to be clear what I mean by this. It doesn't mean that you shouldn't go out and buy hardware for these purposes. What I'm saying is that it's a little difficult to integrate these pieces on your own at this point. Unfortunately, it's the only way sometimes that you are able to do it. There is no, you can't go down to Best Buy and buy yourself, an AI and machine learning, box to put into your data center today, but you will. And various vendors are working on this, and we should see some great improvements in this in the near future. Something that came out in the data, and we have a separate report that's attached to this. You'll be able to dig a little bit more into this. Is the changing needs for operations teams around this? It's not just simply throwing more GPUs into servers and calling it a day. There is significant amounts of work that needs to be done around automating operations to better handle the architecture changes we're discussing here. And certainly there's also a certain amount of work that needs to be done about the skill sets of those operations folks. And that's a general concern and issue that's been brought up for the last decade or so around things like DevOps. And lastly, don't ignore risk management. This is another thing that shows up in the report, and it shows up in our data. But if you ask people, what are you most concerned with outside of hardware, it's usually a response around the risks associated with AI machine learning. Not necessarily that the bots are going to take over, but more along the lines of, I know that there's probably PII in this. If I'm going to be having a truly hybrid and agile workflow where, I can move these workloads around, I need to make sure I'm on top of where these workloads are at any given moment. So you need to have a proper set of governance and compliance procedures around this, and this applies just as much to AI machine learning as it does to any kind of infrastructure as code. And with that, I want to thank you. I'm going to be passing off to Micron in a second, but you will see the research that we just discussed, the custom research, and Forrester obviously has additional research in this vein, and you could follow me on Twitter if you'd like to watch my travels in the AI and ML world, as well as things like automation and infrastructure as code. And I will hand off to Micron now.
Thank you, Chris. We really appreciate the great work that you and your colleagues at Forrester have done to dig into the role of memory and storage in AI workloads. And definitely want to thank you for your expertise and for taking your time to share your insights on this topic with us today. My name is Eric Booth. I'm a business development manager at Micron, and I'm here in Austin, Texas today at our Customer Solutions Lab with Wes Baskey. He's a principal storage solutions engineer, and Wes, we've heard from Chris that people on the ground doing AI work, building these AI-capable systems they overwhelmingly believe that architecting their systems around memory and storage are really critical to accomplishing their goals. So you have a lot of experience analyzing AI workloads in your lab. Is this focus on memory and storage a new development? Why haven't we heard more about this before?
Yeah, that's a great question, Eric. So I actually have some data that talks about this a little bit, but the short story is we haven't really been talking about storage and memory and how that impacts AI workloads until recently. And if we look at this data, it's pretty easy to tell why. So what I've got here is the training performance in terms of throughput, images per second, for training a specific model, in this case ResNet 50, on a specific data set, in this case ImageNet, a data set of 1.2 million images. The clock's in around 150 gigabytes. If we go back to 2014 and look at the best GPUs of the day, the K80s, and we look at a system that has 8 of these GPUs, so a pretty beefy system, and we train this model on this data set, we find that we really only need about 50 megabytes a second of disk throughput to support what the GPUs are able to do. Now, as we move forward a generation to 2016 with the release of the P100, a similar 8 GPU system is suddenly driving much more storage performance, 150 megabytes a second. That's still not difficult to architect. That doesn't really give you any big challenges. 150 megabytes a second is rotating disk territory. That's still pretty easy. Once we move to the next generation, the V100s, and then add some software optimizations to the different frameworks as well as the algorithms on top of that, suddenly we're in a place where architecting is a challenge. We're at nearly a gigabyte a second for this model on this data set for the system going through the training process. If we were running inference, that number would be about twice as high. So now it's easy to see why we're talking about this now. This is something that we knew was coming, but we've been able to sort of kick the can down the road as we were going. But now the problem is here. We need to architect solutions intelligently so that we ensure that we have enough storage performance to fully utilize the systems that customers are purchasing.
Yeah, this is really interesting data, Wes. It's kind of eye-opening to see how, as these AI workloads have evolved, and as the hardware that runs them has evolved over the years, it's really put a real demand on the storage system. So we've talked a little bit about storage and how that plays into AI workloads. Have you taken some similar data around memory?
I have. So I actually looked at basically the same model, same data set, and I used basically the right bar with the V100s and all the software optimizations. And I explored what happens to your training workload as you either decrease the memory that's available or decrease the storage throughput that's available. And the way that I did that for the memory side, I'm looking at an amount of memory such that only half of your data set could fit in memory. That's going to prevent caching from being able to just hold the whole thing. And on the storage side, I did this the same way that the cloud providers are going to limit your resources to their GPU instances. I set it at 500 megabytes a second and didn't let my disks go any faster than that. And what I found was actually somewhat startling. I did not expect as large of a performance hit as I found. We're looking at a system that if you don't have dense memory and you don't have fast drives, you're at 30 to 40% utilization of your GPU resources. Thankfully, the solution to that is pretty easy. You're going to need one or the other, either dense memory or fast drives. One of those is critical to getting efficient use of your compute resources. And ideally, you're going to want both. And that's very classic for most workloads that we study. A lot of memory and fast drives is going to give you better performance. In this case, at least one of them is necessary for reasonable performance.
Well, this is a great example, Wes, of how not architecting a system with memory and storage in mind can really hurt the performance. And in this case, you have some pretty expensive AI accelerator cards in your lab, and if the memory and storage aren't architected appropriately, they're just going to be sitting there idle, aren't they?
You're absolutely right, Eric. And that's not something from a business perspective that you ever want to be talking about. You don't want to need to show that your very expensive hardware is running at minimal utilization.
Awesome. So one of the key things that Chris pointed out when he was talking to folks doing AI is the need to re-architect to get memory and compute closer together. So we're talking about system memory here in this example, memory that sits off of the main system bus that talks to the CPU. One way of moving memory and compute closer together that's really been popular now is moving the AI workload off of the CPU and onto a GPU or another accelerator that makes use of near memory. I understand you have some data around near memory and its impact on system performance.
I do, yeah. And to keep things consistent, I'm looking at the same basic model, the same basic data set. Although here, what I did is I tested for a given model how performance changes as I increase the batch size. And in this case, batch size is how many images I'm sending to the GPU at one time to process before it updates the model. And the 3 lines that I have on this chart represent 3 different versions of the ResNet model, ResNet 50, 101, and 152. And those numbers correspond to the number of layers. So that's sort of a placeholder for the complexity of a model. And each of these lines, you see a dramatic increase in the beginning where increasing batch size is going to increase performance for training that model. And eventually, each of these lines ends. And the line ends where the batch size is no longer supported. We tried to feed too much data to the GPU, there wasn't enough capacity, and the training process will actually fail and stop. So what we're seeing here are 2 main takeaways. The first is that larger batches are going to give you increases in performance, and you need more memory to support those larger batches. The next piece is that as a model gets more complex, it's going to use more memory just to hold the model, which gives you less memory to hold the data that you actually need for training. Now, the system I'm using has a lot of memory per GPU, 32 gigs, but there's a host of other GPU and accelerator options available with less memory. So if you were looking at one of those systems and maybe poorly architected for your use case, you could run into a situation where a model is too complex with not enough memory such that you can't train that model at all. And that's not a situation that you want to put your developers and researchers in. So as a first case, you're going to want to ensure that research and development has enough memory to test any model that is reasonable for the use case. And then from there, you're going to want to tune to get as much performance as possible when you're actually doing your training or inference workload.
Yeah, this is great work, Wes, and really interesting insights. I know when I talk to data scientists and application developers who are developing these deep learning models, they certainly don't want to be limited to the types of models that they can run, to the sizes of batches. They want to be able to use the parameters, the models, the batch sizes that really optimize their application for deployment.
You're absolutely right. And all of the data that I'm looking at here, I was really just looking at how memory density, the amount of memory that you have, impacts performance. And I sort of glossed over an important piece here, which is memory bandwidth. And I believe you've got some data that you're going to share with us that discusses how bandwidth can impact performance.
Yeah, absolutely. Memory density, making sure you have the right amount of memory for your application is critical. But like you mentioned, there's a lot of other metrics when it comes to memory that people need to think about, including bandwidth, like you mentioned, and latency and power consumption. But yeah, I want to talk about memory bandwidth and really mention some of the key growth drivers for memory bandwidth products. And this is the AI accelerators. Really, AI accelerators are driving the demand for high bandwidth memory products. And it's pretty well documented that you can receive amazing performance gains on many AI applications by moving to these accelerated platforms. But what I think is a little bit less well known is the role that memory bandwidth plays into this. And so to illustrate this, I've borrowed some concepts from literature called the Roofline Model. And in the Roofline Model, it's a way that you can kind of analyze an application and a system to look for performance limitations. And so in the Roofline model, on the y-axis is the compute operations per second, and then on the x-axis is the number of compute operations that are performed on each byte of data from memory. This is sometimes called computational intensity. And you can plot your system on this graph, and it kind of looks like a roof line, where the horizontal part of the roof line represents the maximum compute capability of the system, and the slanted line represents the maximum memory bandwidth. And on this chart, I've plotted some examples of CPU system using DDR, a GPU system using GDDR, and an SoC system like a TPU using HBM memory. And on the same chart, you can plot different applications and see if these applications lie either on the memory bandwidth line or the compute line. Applications that lie on the memory bandwidth line, these are memory-bound applications working typically on large amounts of data with relatively few numbers of computations. AI applications very often fall in this category. But now when we look going from the CPU to the GPU to the SoC-based system, it's much more likely that these applications are going to lie on the memory bandwidth line. You can see great performance gains from these different architectures as far as compute goes. And this makes that slanted memory bandwidth limit become a much larger line and much more likely for applications to fall in there. And this is the reason why Micron's really heavily investing in next generation memory technologies, the next GDDR and the next high bandwidth memory.
So Eric, I want to make sure I have this right. So the chart is showing us that as we started out with CPUs, many things were compute bound, and as we increased the compute power that was available at historic rates, going to GPUs and then ASICs or SoCs, with those large jumps, we have seen faster memories go along with those products, GDDR, HBM, stuff like that. But what you're saying is they're not increasing enough, or we have so much compute available that we're still hitting memory bandwidth limits even as we're getting faster memory?
Yeah, absolutely. And I think that's one of the key reasons why, Forrester's data pointed out that, architecting around memory and storage are so critical. And this is a case where, that memory compute interface is a really challenging interface to speed up. And in these applications, oftentimes just throwing more compute power and more cores at the problem are not necessarily going to get you the performance that you might expect.
Interesting.
Yeah, so when we talk about these next generation memory, I think it's really important to kind of take a step back and try and visualize the landscape of where AI workloads are being done. And, Chris mentioned that, this landscape is very diverse, that the AI workloads are not just being done in one place, although today there's a lot being done in the data center. This is where the typical model development and large-scale batch training is happening. But one of the trends that came from the data is more and more of this work being moved out to the edge and to the endpoint. And when we look at this landscape from the perspective of a memory and storage producer, it's really important to us, to see that we know that customers need a very diverse portfolio of memory and storage products in order to support these different workloads and different systems. And so for the next few minutes, we're going to talk about a few of the different applications. We're just going to pick a couple applications from across this landscape and focus a little bit on how memory and storage are used in these cases. Where in the data center is going to demand a certain type of memory and storage and lead to different types of architecture decisions, where out on an endpoint device where there's different constraints like form factor, environment, and power, this would lead to another set of memory and storage choices. And Wes is going to start off with the first example of an intelligent endpoint device.
Thanks, Eric. Yeah, so this is sort of a relatively new category of devices that we've really seen just start to take off. So in the past, IoT devices are dumb sensors that you can place all over and are going to feed data back to a central system. Well, now we've got IoT sensor systems that are able to have SoCs built in with neural network accelerators. This means that we're able to take something like a security camera that would have just stored images or sent it back to a central location, and now we're able to load let's say an object detection model that's pre-trained onto that system and do inference on the device. So now instead of just putting up a security camera and having a system monitoring all of those feeds, you could place security cameras around, let's say, a gas station with an object detection algorithm that's going to tell a system locally what it sees. So if it sees, let's say, a fire or a cigarette or something else that's dangerous, it could trigger an automatic shutdown of the gas pumps. So it's pretty easy to see how that use case can be used almost anywhere. However, it does have really specific requirements and constraints if you're trying to build a system like this. You do still need high bandwidth and high performance memory, but power consumption matters now, and it matters a lot. So does form factor. So for this, you're going to use something like LPDDR4 for the power efficiency while maintaining high bandwidth. You're going to have some embedded NAND products, either SLC or eMMC for the OS and the model and things like that. It's likely that you might want some long-term storage for archiving. You could use something like a micro SD card. All of these decisions are going to be driven by focusing on power consumption and form factor, as well as the industrial ratings necessary to be able to place these devices in production where you actually do things. There's gas stations in Arizona, there's gas stations in Alaska. These devices are going to need to be able to work in any of those situations.
Yeah, thanks, Wes. This is a great example of, one of these outdoor kind of intelligent endpoint devices that have really unique constraints as far as the memory and storage needs. So the next application of AI that we'd like to focus on is autonomous driving. This is one that gets a lot of attention. Chris mentioned he saw a driverless car driving by his neighborhood the other day. Autonomous driving is a platform that kind of has some unique demands for memory and storage. One of the key demands on memory in an autonomous driving platform is just raw bandwidth. There is a huge amount of data that needs to come into an autonomous vehicle to be processed in order to allow that vehicle to make decisions in real time. One of the popular autonomous driving platforms, NVIDIA's Drive platform, it requires more than 1 terabyte per second of total memory bandwidth on a relatively small, tightly integrated form factor. And this creates some really unique challenges in order to get this amount of bandwidth on an integrated system like this.
Now, Eric, when we were first doing our research and putting these slides together, and I first found out about the NVIDIA Drive AGX system, I was certain we had a typo in here. A terabyte per second of memory bandwidth is a pretty ridiculous number, especially for something with this form factor and power consumption limits placed upon it. But it's accurate. It's a terabyte per second of memory bandwidth. But as I started thinking about it more, it made sense because these autonomous vehicles have a dozen or more 4K video streams. They're going to have other sensors like LiDAR, radar, rangefinders, different things like that. And being able to process all of that, that data needs to come into the chip, into memory, get processed, and go back out. And the only way you can do that is by having, one, enough memory, and two, memory at a high enough bandwidth to support what you're trying to do, right?
Yeah, absolutely. And that's just one of the challenges. We chose to focus on memory bandwidth, but an autonomous driving application has many other challenges like power, as you mentioned, reliability, and security. And so this is an interesting area to keep an eye on as far as how the systems are architected around memory and storage. And, autonomous driving is another interesting example of AI because of where it lands in the landscape. It's one of those applications that kind of straddles the line between an edge computing device and an endpoint device. And now you've chosen to focus on a couple of more traditional smart edge computing devices. Is that right?
Yep, you're absolutely right. So I've got two use cases that I'm going to discuss, and on the surface, they sound pretty similar. Each of these use cases is actually using an FPGA that implements neural network models to run inference at a pretty high rate. The first one is part of a project that Micron has had accepted with Open Lab. We're working with CERN, the large particle accelerator in Switzerland. Now, if you're not familiar with particle accelerators, the main thing to take away is that when they're crashing these particles together and things are going flying, they're generating enormous amounts of data. In this case, they're generating 5 terabytes per second of data at one of these sensor locations, and they've got many of these at the particle accelerator. So to be able to handle that, we're looking at doing a proof of concept with FPGAs implementing these models that have a high amount of memory that's throughput focused to try and manage this stream of data. And to put it in context, 5 terabytes per second is roughly equivalent to 40 100 gigabit Ethernet ports at full saturation 24 hours a day.
Wow.
It's a purely outrageous number. And FPGAs are one of the ways that we think we're going to be able to solve this problem. And again, that's focused on having a large amount of memory attached to the FPGA to handle the incoming data, cache it, run through batches, and really maximize throughput. The next use case is medical imaging. So imagine that you've got a CT scanner and you want to be able to process each image that comes out of that and run against multiple models. Let's say a model to detect a fracture or a brain hemorrhage or a tumor or whatever other models are being developed. Well, to do that, you're not going to want to wait for multiple images to be taken from multiple patients to queue up and run through the process to be throughput focused. Instead, you're going to take each individual image and immediately start processing it. So for that, we don't need as much memory with the system, but we do need high performance, low latency memory to ensure that we can get each image processed as quickly as possible so that the medical professionals have the data necessary to make decisions.
Well, thanks, Wes. These are two really great examples of AI being deployed at the edge in areas like science and health, two really exciting areas where AI has potential to make huge impact.
Mm-hmm.
So to kind of conclude our tour of the AI landscape, I thought we'd just kind of bring things full circle and back to the data center and the cloud and talk about some of the challenges associated with memory and storage choices there. Chris mentioned that this is really where a lot of the AI work is being done today, and that primarily in the cloud using third-party services, that's where all the training is happening. But we're moving towards kind of a landscape where organizations are going to be doing this both in the cloud and on-premise in their data center. And whether you're building out infrastructure on-premise or you're making choices about what cloud services to use, there's a lot of choices out there. The data center is very heterogeneous now. We have traditional CPU hardware that's available, of course, but many types of AI accelerators that we've talked about today, from GPU, ASIC-based, and FPGA-based. And with all of these choices that people have to make, it could be easy to neglect the memory and storage architecture choices. But some of your data that you've shared with us today from your lab and the results from the survey show that people really are thinking about this. People are really concerned about making sure they make the right architecture choices to make sure they have enough system memory, they have enough near memory, that they have the right kind of storage, enough storage with the right kind of performance, and as well as the right kind of performance out of their memory. And architecting with these things in mind is really critical in the data center. So one example of this is Micron. Actually, in our data center, we have some customized hardware that allows us to deploy AI for our manufacturing process. We use deep learning models in order to do defect analysis and manufacturing anomaly detections. And this really helps us to improve the quality of our products while also reducing costs. And I think this is something that we're probably going to see a lot more of companies that are deploying AI in order to help them make their products better. And it's really interesting in this case with Micron being a supplier of memory and storage products that then go back in to the infrastructure to enable even more AI to happen.
All right, Eric. So I think we're done throwing new information at everyone for now, right?
Yeah, I just want to mention if anyone's interested in learning more about how we use AI in our fabrication process, there's a link here on the slide, so I encourage people to go read that if they'd like to learn more.
Yeah, and I'm going to reiterate that. It is actually a really interesting article. We have quite a few details about where we're using different processes in our manufacturing facility. And it's not just to improve reliability of products and the production capacity, but to also improve employee safety, all of which are good things, and it's really exciting to see what we've done in that.
Yeah, so that kind of wraps up our tour of the AI landscape from the perspective of memory and storage manufacturer. And we really hope that this is useful, and we appreciate everyone tuning into the webcast.
All right, so let's take a step back and just make sure we're all on the same page. The first things that we covered were different benchmarks that I ran, exploring different aspects of architecture. I looked at how over time architecture has changed the requirements for storage. I looked at how the amount of memory and the performance of your storage is going to impact performance, as well as how much memory on your actual accelerators is going to change things. From your perspective, what's the main thing you want our listeners to take away from those slides?
Yeah, I think the data that you shared is really interesting, and I think it really went hand in hand with the data that Forrester presented, in that people are understanding that we have to architect around memory and storage in order to maximize the potential of these AI workloads. So we also, Wes, talked about kind of the landscape of AI and where AI work is being done today. What's your takeaway on that?
Yeah, so I feel the data that we provided really goes along strongly with what Forrester showed customers were already thinking about. We looked at the data center, we looked at smart edge, we looked at IoT, we looked at weird devices like autonomous vehicles that sort of bridge the gap between smart edge and IoT. And the real takeaway is that AI really is happening everywhere. When we talk about an AI workload, that's almost meaningless given the number of places that AI can happen and the number of different ways in which an AI workload can exist. So to me, that's really the takeaway, is that AI is happening everywhere, from the data center to the edge to the endpoint, and that really drives home the point that you need to consider storage and memory and your use case when you're architecting your solutions.
So thanks, Wes. So at Micron, our vision is to transform how the world uses information to enrich life, and it's really exciting to see how AI is doing this. And if anyone on the webcast would like to talk to any of our experts like Wes about how you can best architect your systems around memory and storage in order to maximize the potential of your AI workloads, please reach out. Thank you.
Great, guys. That's awesome. Thank you so much. This is Jay again. Eric and Wes and Chris, thank you for giving us that insight. Certainly it sounds like that if you're architecting a solution out there for AI, you want to make sure you keep the memory and storage in mind, because that's going to really drive the performance that you want to get. And the second point there, that AI is happening everywhere, and that Micron has a portfolio of products and expertise to really help with those AI solutions. Good summary there, Eric. Really appreciate you taking advantage of that. Let's jump to a few questions. There were a few coming in, so appreciate the feedback. We got about 5 to 10 minutes here to throw a couple up. So I'm going to start with one question here. Let's see. Let me throw this over to Chris. Let me see where. Let me try to find where this is. So did anything surprise you from the data in your custom research? Did you see anything that you didn't expect when you were doing the evaluation and getting the survey and the feedback back?
Yeah, I think the most surprising thing was just the level of maturity people have in terms of understanding the technical challenge here. I really kind of expected folks to look at this and say, I need more compute capacity, or I need to address this through a software concern. And certainly that's part of the AI and ML, challenge. But to actually call out and have it show at the top, bring it up to the top that storage and memory are concerned. And I want to be clear that when we did this custom research, we weren't going after specifically people that were just looking at storage and memory. We're looking at people that are responsible for, again, these complex data workloads and building out the AI and ML architecture. So for them to say, this is the top thing on my list, obviously it plays to Micron very well, but it also plays to just the general consistency of that group saying, look, we're at a stage now where we're no longer POCing this thing. We need to make this a mature approach, and we need to re-architect in order to pull that off.
Great. Thanks, Chris. Eric, I'm going to throw one your way, and I guess there were some comments made that the landscape has changed and that memory and storage are a critical path for making performance in AI. Eric, can you explain what has actually changed to make memory and storage now in the critical path?
Well, yeah, that's a great question, Jay. We looked at the landscape and we looked at how diverse the workloads are and how they're being done everywhere. We also talked about some of the AI accelerators and how they've really increased the compute capability for an AI workload. And I think, kind of the combination of having the capability of doing a lot of compute, many cores of processing being thrown simultaneously at these problems, as well as, a diverse landscape of different form factors, different environments, different specific applications, has really, it's really led to a situation where, there's opportunity for real differentiation among these different products and workloads for the types of memory and storage products that are going to be able to optimize that solution. And so I think it's kind of the combination of those factors that have come in and made memory and storage such a critical piece of enabling AI today.
Great. Thanks, Eric. Wes, I'm going to throw one at you. You talked about different models, model parameters, batch sizes. In your experience and from the examples that you have run in the labs, is there a best practice to optimize memory and storage for AI?
Yeah, so there's a few sort of processes you can follow to figure out what your best solution is going to be. So on the earlier slide where I was talking about having a lot of memory or a low amount of memory, fast drives, slow drives, what I was looking at there was limiting memory to a % of the data set and the storage to a % of what the system had been using. And then on the next slide, when I was looking at batch size, I was scaling batch size and just looking at throughput. So on that part, that's not how you would generally do that in an actual production environment. There is going to be a place where if your batch size gets too big, you start grouping too many items together and you don't get as much information out of those. So even though you're increasing total training throughput, you're decreasing the rate at which you're converging on a solution. So for something like that, it's really just going to be kind of trial and error. You're going to run a test for a while, see what your rate at which you're gaining accuracy is, and see how that is over time instead of per epoch, and measure how long your epochs are taking. It's relatively complicated. Well, it's not complicated, it's just a little time consuming. On the inference side, though, that's thankfully easy. you just do a larger batch size. The largest batch size possible is going to just increase your inference throughput, and there's not really a downside to doing so other than each piece of data has a longer latency because it's part of a batch. And a rule of thumb on the training side, I generally saw performance decrease in terms of converging to a solution if my batch size was more than 0.1% of my total data set. So long as I stayed under 0.1%, I could increase my batch size up to there and continue to get increases in performance.
Great, thank you, Wes. Thanks. Chris, got one for you, and this is kind of a thought not so much about the architecture, but where the data is being processed. Should we not look at reducing the amount of total overall data movement, meaning from the edge to the data center, between processor and the memory?
Yeah, I mean, we absolutely should. I think that, and we probably have a few telecom folks on the call, so I don't want to be too negative about this, but a lot of people kind of look at 5G and saying that that'll solve this because we're all of a sudden we have all this bandwidth to send all this data around. But the reality is that it makes no sense to do that, right? So in the edge research that I focus on, there's a tremendous amount of local processing that's occurring specifically to rationalize the data and not send it back up to the cloud unless needed. So an example would be smart traffic lights in the city. There's no reason to send all that data up to a public cloud to process it. In fact, you don't want to from a latency perspective. So it's done locally at the edge in the city itself, and then that data is sent along to the cloud at the end of each day, so that way different cities can compare and contrast different approaches to running the traffic lights in a different pattern to address traffic. So to answer the question, yes, we absolutely need to take advantage of these things so we're not sending as much data up and down the chain.
Great, thanks. Hey, Wes, I see that you answered the one I was going to ask you next. What is meant by fast diffs? Are you referring to NVMe disks? That's a good clarification for you to take.
Yeah, I was typing the response in case we didn't have enough time to get to it. So for the test that I ran, fast disk in this case was unlimited access to the underlying storage system. And the underlying storage system I had was 8 NVMe drives in RAID 10. So for reads, I had full bandwidth of all 8 drives available. Theoretically, I think that would get me up to about 25 gigabytes a second of aggregate throughput. For my testing, the highest that I ever got up to in the lab for the image recognition was around 2.5 gigabytes a second. And then for the slow disk, what I did is I basically just used Docker container QoS to limit the container to 500 megabytes a second. And that's actually real similar to how the various cloud providers are going to provision virtual disk for the GPU instances. They're going to have a bunch of solid-state drives that are set up in a large array. You'll carve out a portion of capacity as well as a QoS maximum throughput available. I know there's virtual disks out there that are 250 megabytes a second. Some are 500. There's some new ones that are ultra-fast direct access to NVMe that'll get you a couple gigabytes a second. For the most part, if you've got your data organized properly, so it's not just a bunch of small files, but it's in a format that you can do bulk large block reads, you can just add those numbers together and figure out what your performance requirement is, provision enough virtual disks in whatever way you do, and you should be able to meet your storage requirements.
Great. Thanks, Wes. So I think that about concludes all the time we have for questions. I really appreciate the questions that have come in. These are very thoughtful. I just want to make sure I go back to let everybody know. All those on the call who have attended the call, we will go ahead and send out an email with the study that was performed by the Forrester team, as well as the results there, as well as a link to this webinar so you can go back and rewatch if you need to. There's also a link on the slide right now if you'd like to have more information. Micron.com/insight is a great resource for you to do that. I'd like to, at this point, thank Chris and Eric and Wes for their time and dedication to deliver some great content. And we hope everybody on the webinar got what they needed out of this, and there'll be more coming from Micron. So thank you so much for your time.
Thank you.
Thank you, Jay. Thank you, everyone on the webcast.